We have a potential energy curve of an object that's 20 kilograms. At a distance from 0 to 300 meters, the object has 5 to 2 joules of energy. From 300 to 450 meters, the object has a constant 2 joules of energy. From 450 to 600 meters, the object has 2 to 3.5 joules. And from 600 to 700 meters, the object goes from 3.5 joules to 0 joules. The object's total energy, indicated by this dashed line, is at 4.5 joules. The dashed line crosses the potential energy curve at 200 meters. We'll call this point where it crosses point A. Here at point A, the initial velocity is given to be 0, and so our kinetic energy at point A is also 0. The potential energy, which is the height of the curve at the point, is 4.5 joules. For a potential energy curve, the total energy is equal to the potential energy plus the kinetic energy. And so we can say that the total energy is equal to 4.5 joules. Here at point A, the position is 200 meters, and because kinetic energy is equal to 1/2 mv squared, velocity at point A is also 0. Now let's examine the speed at point B, which is at 400 meters. By rearranging our previous equation for total energy, we can solve for the kinetic energy. Our total energy is known to be 4.5 joules, and our potential energy is measured to be 2 joules. By subtraction, we can find the kinetic energy at B to be 2.5 joules. Our goal, however, is to find the speed at B. And so using our equation for kinetic energy, we can plug in terms and solve for V. We found that the speed of the object at point B is 0.5 meters per second. Now let's find out what the force on the object is at point C. On a potential energy curve, force can be found as the slope of the curve. The slope of the curve is just its tangent, and so we'll look at the tangent of the curve at point C. Point C is at the peak of the potential energy curve, and so its tangent and slope is 0. Because the tangent at C is 0, the force on the object at C is also 0, and so our final answer is 0 newtons.